So let's talk about ancillary equipment. Yeah, I mean, you know, that stuff. Yeah. Well, maybe you don't know what that means. I'm here to tell you. But what I think I'm going to start with is what not ancillary equipment is, or what is not ancillary equipment. I've got some stuff here. Hey, this is a little compressor. It's a little tiny, kind of small compressor, but it's a compressor. It's got a little pump in it. It goes brrr and pumps. I've got another one here. Actually, this is even a smaller one. Pretty cool. That's a compressor because there's actually a pump in here and it's doing some compressing. We're going to get into compressors. We're going to do like a whole lecture on just compressors, but I mean, they're not ancillary equipment. This is really cool. This is a little pneumatic pump. It works. It's so amazing. We'll actually take this thing apart when we do the pneumatics lecture. And just hold on a second. Let me show you another compressor. This is my little lab compressor. It's just a small little guy. It's got a big tank on it, or actually a small tank. It's got a regulator on it, and it's got a compressor on it. It's got a bunch of other things, and we call this whole thing a compressor. So that's not ancillary equipment either. Wow, so are we ever going to get to ancillary equipment? Well, actually, no, not just yet. Here, this is a pneumatic actuator. Okay, it goes back and forth. We've talked about these, and I got this other big pneumatic actuator here, and you know, we did a whole lecture on pneumatic actuators. Are they ancillary equipment? Actually, no. I've got this cool little spray can. Yeah, this is actually really cool. This is a paint can for spraying. What do you call it? Spray painting? It's actually different. It's got a totally different name. Yeah. So I don't remember what it's called. It's this thing it's the little paint thing. It'll come to me later, and then I'll blurt it out in the middle of the lecture. So you put this guy on here. And then there's this little button here where it's like, just stop this. And then there's a little button here, psh, 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 and you can put paint on stuff. That's not ancillary equipment. That's a pneumatic applicator thing. It's a spray paint can. Oh, wait. Oh, this is a valve. This is a DCV. It's an electronic DCV, actually, and it's only a one solenoid DCV, so there's a spring in it, and that has a natural state. By the way, that's a 2-3. It's only 3 ports on this. Actually, if you want to get into maybe outside the box thinking with this stuff, I did a video with this lab, actually. You can search it on my YouTube channel. It's called exhaust, something about using exhaust backwards or something, exhaust port. Type exhaust for searching. That's not ancillary equipment. This is another DCV. It's also not ancillary equipment. Do I have any other non-ancillary equipment here? Wait, what about this? Oh, it's a pressure gauge. Huh. That's ancillary equipment. Actually, no, this is really cool. This is a vacuum gauge. No, it's just a broken pressure gauge. Okay, it's just broken. So that is ancillary equipment. Okay, so welcome to ancillary equipment. What about this guy here? Yeah. This guy is an accumulator. It's a kind of small little pressure tank. That is ancillary. So the main stuff in a pneumatic system, the actuators. Actually, this is an actuator too, or this is an air gun, but it's an applicator. Yeah. It applies pneumatic principles. It takes pneumatics and it makes stuff go. This makes stuff go. So this is not ancillary. This is actually a main component of a pneumatic system. Again, that pump is a main component of a pneumatic system. But when we get into these little kind of specialty valves, that's ancillary equipment. This is actually a metering valve. It's called a non-return throttle valve. Really? Yeah. Well, we're actually going to study non-return throttle valves today because we're studying ancillary equipment. Yeah, there you go. So anything that's not the main thing. Actually, here we go. This is a really cool flexible line. This is a really cool flexible air line. That is actually ancillary equipment as well. This is kind of an extra add-on kind of thing. Now, is this a line or a hose or a tube or I don't know. Well, we'll get into that. So here we go. So let's just jump into, I've got a PowerPoint here, and let's just jump into things, and we will discuss a little bit more about ancillary equipment. So the first thing is, I got to point out this adjustability thing. I mean, we talked about that. Actually, I mentioned this symbol in the lecture for actuators. And dude, this just means that something is adjustable. And obviously, we see this in electronics and all other kinds of disciplines. Pretty standard symbol. Let's move on. We've got all these other things that we add on to kind of the main core of a system. And these guys, anything with a diamond-shaped symbol indicates something that conditions the air. These are all different types of conditionings of air devices. And we're going to go into those later. We're actually going to do a whole lecture on this stuff. So there you go. I just wanted to kind of heads up. This is an ancillary equipment as well. We got air dryers and filters and strainers and lubricators and all these other. Oh, that's a really cool symbol. A heat exchanger or aftercooler. Cool. I love thermodynamics. It sounds thermodynamic. Yeah. So there you go. Ancillary equipment. Oh yeah, gauges. I did mention a gauge. Now this is interesting. We have like 3 kinds of gauges here. In pneumatics, we pretty much have 3 kinds of gauges. There you go. So one indicates a pressure, and that's, we call it gauge pressure. And also the other indicates pressure too, but it's a vacuum pressure, and it's also actually a gauge type pressure. The gauge pressure is a differential pressure. Yes, and that's, I mean, you guys know that from the very first lecture. When we're looking at a gauge, it's telling us the difference between the pressure inside a vessel, whether it's actually this accumulator, we could put a pressure gauge on this accumulator, or it's the tank on my compressor, or it's some other tank somewhere. Sometimes we call something called an air pig, which is like a portable air tank you can kind of carry around with you. However that is, it's going to have a pressure gauge on it. The gauge pressure, whether it's for a vacuum or for it's just for like pressurized air, is telling you the difference between what's inside the chamber and what's out in the atmosphere. That's what a gauge does. So we've got 2 kinds of gauges. One tells us about pressure and one tells us about vacuum. I specifically kind of really like the vacuum gauge symbol because it's really cool. Yeah, it looks kind of like an upside down anarchy symbol. Not that I'm an anarchist. Okay, cool. So flow gauge, I think that's pretty cool. It kind of looks like a what do you call it, like a ball? What do you, tennis ball? That was what I was looking for. It's a tennis ball. So that's kind of cool. It's got that symbol, but you can look at it as though the flow is going through here, and that's kind of testing the flow. It's kind of touching into the flow, saying, hey flow, tell me about kind of your principles. What's going on? Yeah. So there you go. That's just a gauge, and these are ancillary equipment. Now we get into a check valve. Now I've got some check valves here. Where did they go? Where did they go? There it is. This is a check valve. This is a really low pressure check valve. This is a really small check valve. It's actually for high flow, low pressure. And the cracking pressure on this is very small. I can actually crack it with my mouth. And by the way, guys, I know this actually only through practice, that the pressure in your mouth, you can generate about 3 psi in your mouth, maybe 2.5, 3, maybe some people can do a little bit more than 3. But I know that because the cracking pressure, yeah, that's a term, cracking pressure, on a lot of the check valves that I've used over the years is around 3 psi. And I can crack them with my mouth, but just barely. But this thing's really easy to crack. Wait a second. Whoa, it won't crack. It's because I'm blowing it one way. If I blow it the other way, it will crack and air will flow through. Ready? Now I have to keep blowing for it to stay open. And actually, I'm actually losing a little bit, losing energy, kind of like a resistor, or actually almost like a diode, where you have a voltage drop across a diode. There's actually a pressure drop across this diode, but it's a pneumatic diode, and we call it a check valve. Yeah, lets air go one way, but not the other. I could blow as hard as I wanted, and actually the more pressure I blow, the harder and harder it seals. Let's actually take a look at mechanically how this thing works. What's going on here is that we've got kind of the interior view of a check valve. We got a spring over here, and then there's a ball in here. Now, this check valve doesn't actually have a ball in it. It's got a little flap. Lots of different kinds of check valves, but generally this is how they work. And industrial type check valves are going to be, like this. This, again, this is for low pressure, a high flow rate, and this would be used, actually this type of thing is used for medical devices. At least that's what I used it for. I designed and developed some medical devices, and I used a bunch of these. Also, these might even be like on an air mattress or kind of low pressure, high flow kind of stuff. So I think the maximum pressure for this is probably about 20 or 30 psi. I wouldn't put it more than that. Let's just take a look at this thing. So I've got a ball in here, and I've got this seat. Now, if I were to push this ball up against the seat, if I had something that was pushing it, say some pressurized air, pushing against this ball, it's going to seal that against there. And the more pressure I put onto that, the stronger the seal. And because I need a stronger seal for higher pressure, actually I get it because I have higher pressure, which requires a stronger seal to hold back, which is actually generated from the higher pressure. So as you push it more, it actually seals more along here. But if I were to push air this way, then this thing just moves. But as you can see, there's a spring here. And that is all about what the cracking pressure is. So the cracking pressure is the pressure that's required to actually push that spring aside and squeeze that spring. That's force, right? You're actually doing work there. You're actually doing work. So you actually need some energy to crack that thing. And just like a diode, you need a certain amount of voltage to crack the voltage, to crack the diode, to allow current to flow through it. You're always losing that voltage drop across that diode. So in lies the voltage drop over here, which is actually pressure. Yeah, and we're going to lose a small amount of pressure. So if the cracking pressure on one of these things is 3 psi, you're going to lose that 3 psi. So in the end, if you need, I mean, you're probably just going to be dealing with 60 or 70 or 50 or 80 psi. If you lose 3, it's not a big deal. But you have to think about that too. And that if your pressure regulator is set to 25, because you need 25, but there's a check valve somewhere in between, you may only get 22 on the other side, or maybe 23 or somewhere in between. So you have to think about that. But these guys do have a pressure drop across them, and they work like this. Now, the other thing I want to talk about before I move forward is an NPT, National Pipe Thread. You will find that all of these pneumatic things, I was just about to grab an NPT, I don't have one. Ah, there it is. So that's an NPT. This is a national pipe thread. It's actually tapered. It's pretty cool. It's actually got a little bit of a taper to it. And this thing's made of brass. And what happens is an NPT is designed specifically not to hold tension or deal with torque or compression. That's not its function, like most threads are. The function of an NPT is to seal a pneumatic connection. It actually creates a seal where air can't sneak by. For one thing, you can see there's a little bit of white on there, yeah, and that white is the tape, the Teflon tape that's on there. But this thing's tapered, and as I put it in, it actually slightly deforms. Yeah, and the female part of that also deforms slightly. So note, you can only undo this and put it in and undo it and put it in so many times before it just fails, because every time you put it in, you put it a little bit further than the last time you did, and you're deforming it. And if you do that too many times, it will just completely deform and it will stop working because you can't put it in any further. But you will see that when you do put these guys in, as you can see, there's a little bit of a white line there. That's the Teflon tape that's left. So when I put this into something, I put Teflon tape all around it. I put it in, and when I took it out, the Teflon tape that was from there to there kind of disappeared. So I've still got this much thread left. So I can probably still use this maybe 2 or 3 or maybe even 4 times. But after that, it's gone. I may have to replace it. So interesting kind of note about the concept of an NPT, a National Pipe Thread. It's a very common thread. It's on all kinds of, any kind of pipe that requires a pressurized something in it, whether if it's air or fluid, you're going to see an NPT. And how we use these things essentially is there are many applications where we want the air to go this way, but we don't want it to go this way. It also works with fluids as well. You might be able to think of more applications for fluid, but we are studying air, so let's continue with air. Essentially, what we want to do is we can use this for safety applications. Big deal for safety applications. We're going to go into that a little bit later in this discussion, but essentially I want to ensure against gravity, and we will see there's a really cool type of check valve we use for that. And then we also want to prevent hose whip, and hose whip is a really big deal. It's actually really dangerous, and it can actually kill people if there's enough pressure and the hose is really big and really heavy, or it can just hurt you. And I've got whacked by a hose before, and it's not fun. So we have something called a safety check valve that we will discuss in a minute. But essentially what we want to do is we want to use a check valve to stop back pressure getting into a system, right? Any kind of compressor that's actually pushing air out. For this guy to actually push air out and put the air into a tank, there's going to be a check valve in between, because every time this does a little pump, it pushes just a little bit of air out. It goes into the tank. We don't want that tank going back in and stressing this thing out. So there's actually a check valve there. It doesn't allow the pressure to go back into the pump. And we also can mix different gases in between using check valves. So if I had two gases going into one hose, and I didn't want this gas getting into this hose and this gas getting into this hose, let's say I was mixing oxygen and hydrogen, or oxygen and acetylene, or oxygen and some other thing that's actually quite explosive and flammable, I don't want those connecting or getting back into each other. So I'm going to put a check valve on one line, a check valve on the other line before they meet into a T and go on, and I have a mixture going on. Controlled mixture. There you go. And also, right, so for rotary actuators, I only want the thing going one way. I don't want it going the other way. So I don't want air going out. So if I were to try and turn that rotary actuator, like with a mechanism, let's say I had a rotary actuator this way, and there was a force on it that actually counter-forced that and forced the thing to go backwards, that check valve will help to slow that, or to mitigate that backwards motion. And yeah, like I said, we want to stop that air getting back into the compressor. So check valves are huge. There are many, many other applications for check valves. Actually, this guy here that I just pulled up at first, this is a non-return throttle valve. The non-return part of that name is the fact that there's actually a check valve in here. You'll see them everywhere in pneumatic systems. So here we have something called, like, safety check valve, safety application, where we're holding against gravity. And what's happening here is we have a pilot operated check valve. This is pretty cool. This is a safety application. Safety is like a huge part of all designing that you have to think about all the time in everything you do. So let's take a look at this. We've got this cylinder, and it's lifting some heavy platform. It's a big steel heavy platform, weighs a couple 100 pounds. Now that big steel heavy platform is pushing back because gravity is pushing it down. Let's just say that during the operation of it lifting, for some reason, this valve broke. It's broken. It doesn't work no more. It just broke. Or even this line coming out of the cylinder broke. If that was true, then the air that's caught in there, that's being compressed by the weight, can just vent into the atmosphere. Well, that's a problem, because that's just going to allow that thing to fall. So what we do is we put what's called a pilot operated check valve right onto the cylinder. Actually, it goes right in here. It will look like this. It'll look like this guy, where it threads right into the cylinder. So we don't want to put anything in between this guy and the cylinder if this was a pilot operated check valve, which it's not. It's a metering valve or a non-return throttle valve, but let's just pretend it is. So if this is a pilot valve if it's a check valve that's pilot operated, there's going to be another port on here, and that'll be the pilot port. And how they work is, if you put air into the pilot, it opens it up and it allows air to pass backwards through the check valve. It's essentially kind of the cracking pressure in reverse. Let's just take a look at this. We can see the configuration of this, and the way you read these things is the fact that this air is pushing this ball, the pressurized air is pushing the ball against the seat. And we can see here that this air is just going to push this ball into the seat more, and no flow will go this way. Flow will not go this way. But if I have air pressure here, it will push this out of the way, and it will allow air to go this way. So your question may be, well, if this is this way, how does this cylinder retract? If it's blocking the air, the pilot opens it. Yeah, internally, there's a pilot in there, there's pilot air in there that actually pushes that ball out of the way and allows air to flow kind of backwards through the check valve. So let's just take a look at this. Okay, during the operation of extension, when it's going up, air is going to come out of port 2, and it's going to go here, it's going to go through this, no problem, and it's going to allow this thing to go up. Now, when we want to retract it, what's going to happen is that I'm going to put pressurized air out of port 4. It's going to go to the pilot. It's going to go across here. It's going to crack this open. Now that air is going to go up here, and it's going to go into the cylinder, and it's going to retract the cylinder. The air on this side of the cylinder is going to be able to leave and go through the check valve backwards because the pilot pressure is opening it. So this is an application for a runaway load. Also, in this other situation over here, we have a runaway load application as well. But we've also got something interesting here. I've put in a metering valve. And a metering valve is, what's it called? Yeah, a non-return throttle valve. In this case, we're using it as a metering valve. And this is actually what it looks like. We can see here that I've got a throttle valve, which we'll talk about a little bit later. But a throttle valve, I'll just tell you now, is something that actually throttles the air. So that screw on here is actually going to throttle the air. It just puts a little pin into the orifice of the air going through that area, and it has to going past the screw, and that air has to go past the screw, and the further the screw is into the orifice, then it's not going to allow that air to go through, and it can block it, especially if you turn it all the way, then it actually blocks it completely. So a throttle valve can either completely block air, doesn't do it very well, some air might sneak by, it's not designed to completely block the air, or it allows the air to flow through. It's a flow control valve. Essentially, it's a flow control valve, and we're throttling the air. It's called a throttle valve. Now, over here, the reason this is called a non-return throttle valve is because I have a check valve over here that I've put through, and this is together a metering valve. And what it does is it controls the speed in which this cylinder is extending, and the extension of the cylinder is the one that we want to watch. Again, this guy is going to be connected directly to my cylinder right there. It's going to be screwed right into the port of the cylinder. I'm going to have a pilot on there. So when I want to extend this cylinder, when I want to make it go down, I'm going to have air pressure coming this way. It's going to go through the pilot. It's going to open it. When this does extend, that air can go out and it can go down this way, and it will allow the air to go through. But for some reason, if this whole system fails, if that valve fails, or this line breaks, what's going to happen is that pilot operated check valve will say, sorry, I'm not going to open up. I'm not going to let air through, and it will hold against gravity. It'll hold that weight, especially if it's picking something up that's really heavy. So there's something called a safety check valve. Safety check valves are pretty cool. What's going on with a safety check valve is it allows air to go through. Normally it's just, yeah, you just go, no problem. I don't have a problem with that. I mean, it won't allow air to go back, but you hook it up onto your air source, say your compressor, right on the compressor, or right on a tank. So you put it right at the air source. Here's my compressor, and then it's going to be connected to some tank somewhere. And then I've got a pressure regulator here. Right after my regulator, that's where I'm going to put my safety check valve. And what a safety check valve does is it allows air to go out, but only if there's air pressure on the other side of the line. It only allows air to go out if there's air pressure on the other side of the line. So if for some reason the line itself became broken, or open for some reason. So here we go. So this is hooked up right to my pressure regulator. My pressure regulator is here. I put my safety check valve here in between my regulator and my hose. Now, if this hose breaks, right, I'm using this hose somewhere down the line. I'm using this onto like a jackhammer or some other thing that I'm just running. Could be a pneumatic actuator, could be lots of stuff. But essentially, there's a hose here. There's a hose. And what happens is, if for some reason, whatever the device on the end of here breaks, or if this line breaks, this hose is going to start freaking out. Yeah, it's going to really go crazy, and we call that hose whip. Especially if it's a heavy line, like one of those really big industrial compressors that you see on the street when they're using the jackhammers. That hose, if it breaks for some reason, or if it gets disconnected from the jackhammer, it can start flailing around, and it can like dent cars. It could like kill a human, or like it can do some pretty serious damage. So what happens is the check valve, it senses if there's down pressure that's much lower than the up pressure. So the up pressure here is coming from my regulator, and my down pressure here, if this is open to atmosphere, it's because it breaks, it's going to be really low pressure. It senses that, and it shuts off. It just turns it right off. So it's a safety check valve. There are lots of different kinds of safety check valve applications, and one is essentially to deal with hose whip, and we know that. So wherever actually in an industrial application where we're using a hose, it's always good to put a safety check valve on that hose, just in case whatever is connected to the hose either completely disconnects from the hose or the hose breaks. So that situation is good. And you'll see that in construction sites and shipyards, not so much in automotive, because cars don't really have open hoses, and if they do, they're internal, and they're going to flip around inside the engine compartment or under the dashboard, and it really doesn't matter. Is there pneumatic in cars? Huge. Actually, a lot of vacuum systems in cars, but there are also situations where we have compressed air in cars, especially with trucks. We'll get into that way later. Okay, here we go. So essentially, anywhere where you've got a hose, that's going to something where even if it doesn't have a hose, if for some reason you need to have a system where the pressure can't drop, for sure, pressure cannot drop. For instance, if I did have this hooked up to some system and the hose broke and I didn't have a safety check valve, the pressurized air over here would go run out here and it would vent a lot of air out of the system, and the whole system the pressure would get low. So if there was a robotic gripper that was holding something and it needed that pressurized air to grip and it's lifting something up, and for some reason the pressure in the system just died, it got really low because a line broke open, then it's going to drop that thing. And also any kind of mechanical equipment or clamping operation where you have something that's really necessary, like, dude, I cannot have a pressure loss. It's really important that we don't have a pressure loss. You can put a safety check valve in your system so that if part of a line breaks, or if a tool breaks, or if some component just blows up, if this thing just blows out, right, and the air line going to it is just going to be venting air, then I want to put a safety check valve on there to ensure that I don't get a pressure drop in my system. Now, I want to talk about pressure regulators. I did mention pressure regulators. It was one of those. It wasn't one of those things that I picked up, but I did see a pressure regulator on my compressor. And what's going on there is essentially, these are really cool how they work. They actually have a mechanical feedback in between. The way that they regulate the pressure is kind of in little bits. So what's happening is that I have pressurized air going into my system over here. It's high pressurized air going into the system, and it goes up into here, and there's this little thing called a poppet valve. Now, there's a spring here and a diaphragm, and let's get into the mechanism. Imagine the air going downstream, the air going out. Now that's going to a pneumatic actuator. It could be going to just an air gun, right? Or someplace, whatever it is. If I'm blocking that off, if I'm not running my pneumatic actuator, if I'm not running this thing, then the pressure in that line is going to be pretty stable because there's no flow. It's not leaving to go anywhere. So it's going to be pretty stable. And that pressure is just going to end up being whatever pressure the regulator set it to the last time it opened. So it opens, closes, opens, closes, opens, closes until the pressure is just right, and then it stops. So in this case, my little poppet valve, when nothing's going on down the line here, when there's no flow going out, the poppet valve will be sealed, and no high pressure will go into this lower pressure area. But if I were then to make this thing start running, right? I'm using air, it's venting out, and the flow rate is actually going out of here. So this pressurized air is getting lower. Once that pressurized air gets lower, this diaphragm starts to move, and it starts to go down because the spring right here, this spring is then strong enough to push this down against that pressurized air because the pressurized air is less pressure now. So what happens here is the poppet valve opens, and then air goes in, it pressurizes this area until it reaches a certain pressure. It pushes the diaphragm up against the spring. The spring's got that force pushing down. So that's the kind of the feedback. There's a mechanical feedback loop going on here. So the spring pushes it back down, and the poppet valve, they're kind of fighting each other all the time. And the pressurized air in here, actually more so the pressurized air is fighting the spring. And they balance each other out until the poppet valve either opens or closes and maintains the set pressure. And the set pressure is essentially how much force is being pushed down on that spring. And we can adjust this by turning this dial and compressing the spring more or less and putting more tension onto that spring. Pressure regulators are so very cool. This is the symbol for a pressure regulator, and that's essentially the poppet valve. So we can see there's a little seal in here, and the air just kind of sneaks by. There's also a spring here to ensure that it's actually being pushed up all the time. And then that air is just sneaking through here all the time. And this is constantly opening and closing. If there's flow going out of the pressure regulator, as soon as that flow stops, we stop using this, or we stop using a pneumatic actuator or whatever, then that poppet valve will just seal, and the pressure above it, or the downstream pressure, will just be maintained at whatever pressure it is. That's the symbol for a pressure regulator. And I did mention a couple times, there's feedback. Whenever we have feedback in a valve, we have these dotted lines that are going along here. Those dotted lines indicate that there's feedback in this valve. So there's some kind of automated sensing going on there. In this case, it's just mechanical. In these valves, this feedback is always completely mechanical. There's some kind of mechanical device that's dealing with forces that's moving back and forth to balance out the pressures. So there you go. So that's what this is all about. That's that symbol. And we're going to start using these in all labs moving forward. So yeah, adjusting this guy is going to adjust the poppet valve and the pressure here, and I think that all makes sense. So now let's take a look at a new cool valve called a shuttle valve. Shuttle valves, which we're going to be doing in a lab as well. We're going to be using this as shuttle valve. It's dealing with two inlet pressures, and then my downstream pressure is going to come from whichever inlet pressure is higher. Yeah, so whichever one wins is going to have the air coming out. So essentially, I've got two seals here, so it's kind of like a check valve, kind of like backwards a little bit, or facing itself. Two check valves facing themselves, kind of. What's happening here is that if this air coming in here is higher pressure than the air here, then it will seal this, and then the air will go this way and go out. So essentially, I could put like 30 psi in one side and 20 psi on the other, and the 30 psi is going to flow. Let's say I had some green air and some blue air. My green air was at 30 psi and my blue air was at 20 psi. The air going out would be green air, because my green air is at 30 psi. I think I said that. So the green air at 30 psi is coming out here, and I got green air coming out. My blue air at 20 psi is just stuck in here. But for some reason, if my green air at 30 psi went down to 15 psi, or I just lost it, it just disappeared. It's gone for some reason. The compressor died, or the tank got empty, or something, a line broke, whatever it is, what's going to happen is that this air here, this blue air at 20 psi is going to win, and it's now going to supply whatever's downstream of the output port. So essentially, that's going on. We can use this as a logical operation to say, you know, this or this. We can use this as an or as well, yeah. And we can actually do a lot of really cool logic decisions with just air valves. We won't get into that, but if you want to study that further, that's really cool. You can look into it. But let's just take a look at maybe some further applications here for this. Essentially, what's going on is that if I have two switches running one machine, this switch or this switch, I can use either switch to run some kind of machine. Yeah, pretty cool. It is an or operation. And then essentially, the other thing is that for air brakes. Now, air brakes on vehicles are really cool. They work in such a cool way. Air brakes for vehicles work in such a cool way. You can put your foot on the brake, or there's a button that you can engage the brakes as well. Now, that air pressure, it actually works on a vacuum, but we won't get into all of that. And it's fail-safe. And there's a whole video, if you want, on fail-safe. And I just put the link over here. You can click on this guy and watch that video. I think it's an 11-minute video. But it will help you actually with the lab that has the locking mechanisms in it, because you have to add fail-safe to that lab. And to know what fail-safe is, well, you can go into that lab section, and there's a little link there for fail-safe. There's a short little PowerPoint presentation and a video on that. But I do talk about air brakes there. And air brakes for larger vehicles actually are fail-safe designed. But again, with the air brakes, it's either the pedal that operates the brakes, or there's a push button that operates the brakes. And we won't get into how they work, and they're actually using vacuum, and that's really cool. But there is a shuttle valve that's actually used in that situation. Now, this is one of the labs we're going to do. It's an emergency standby power. And let's just say we have an accumulator here. It's a small tank. If I were to pressurize this with, say, 80 psi, and I had maybe an operation where I needed this thing kind of to go back and forth and up and down, or maybe if it was a situation was opening and closing a door or a gate, or maybe some kind of hatch on a ship or something, or a situation where I had this clamping operation and it clamped and then it unclamped, or maybe there's just maybe a manufacturing process where if for some reason in any of those scenarios that I just talked about, if the air, boom, it stops. The pump stops working, the compressor dies, there's a break in the line, wherever it is, that pressure that's coming into the system, the regulator breaks, the pressure that's coming into the system, it's gone. So in a safety situation, we may still need some pressure. For instance, if I had this operation where I had this thing stamping something and clamping something, and I had to make sure that I had at least one more run so that I could press the button, maybe some override button, to at least retract it, to remove the part that was clamped. Or whatever the situation, I may just want to run my machine for one more cycle. I need some extra air. We can use a shuttle valve and an accumulator, or even just a tank. An accumulator is just a small air tank. So I can put some pressurized air in here, just kind of like a backup battery or a backup system, where if the pressure goes low, if the main system pressure is, say, set to 80 psi and it goes low, and I've pressurized the air in here to 70 psi, then if that main pressure goes and it's gone for some reason, this guy takes over and he wins in the check valve. And now this 70 psi is actually going downstream into the system, and it's running whatever actuators. Now it could be because it's small and there's no compressor filling it anymore because the power went out or the compressor died for some reason. I may only be able to run my actuator 1 or 2 times, but at least I can open that heavy hatch. At least I can lock that door. At least I can close that security gate or open up a gate or some kind of operating mechanism that's for safety, or some fire mechanism, or whatever it is. Often we have a situation where we're like, I just need this thing to work once, one more time. So we can use a safety check valve in that operation with some kind of backup air tank. Pretty cool operation. So we're actually going to do an entire lab on that. So let's move on and let's talk about that application. In this application here, I've got a heavy hatch, and I've got this lifting the heavy hatch. And what I've got here is I've got my 80 psi. There's a whole complicated, there's regulators and stuff down here that we can just imagine. And over here I've got my backup pressure tank, my 70 psi. If this dies and I still need to operate this, there's a manual lever here that opens up this big heavy hatch. If I still need to operate that just once, just to open it up, then I can do that because this guy has enough air in him to actually open this up. Maybe even run it 2 or 3 times, depending on how big that tank is going to be. It's your choice because you may be designing the system. So you have to decide how big your pressure tank is going to be to figure out how many times this can operate. And by the way, we will be studying flow rates a little bit later, so you'll know a little bit about how to calculate that stuff. So high pressure wins, and this is just a further explanation of how this works, but I hope you get that because I did discuss the fact that this is the 80 psi is going to be winning, but this backup pressure is going to win because this 80 psi is going to disappear. So I can still run this, but it's going to be at a lower pressure, but that's okay. It's still going to work for me. Now, throttle valves and throttle valves with lines through them with arrows. I think we know what that means. And then check valves and non-return throttle valves. Yeah, variable non-return throttle valves. You can get a non-variable non-return throttle valve if you wish, but most of them are, I've actually never seen one that is, but most of them are all adjustable. What's going on here is that we can use these guys for metering, and I really do want to talk about metering, and we will get into that momentarily. But the way the throttle valve works is it throttles the air, right? Like I talked about that earlier. There's actually just a screw that goes through kind of an orifice where the air is going through, and it actually slows down the flow rate. It's very much like a resistor. And yes, there is a pressure drop across a throttle valve, but we don't use throttle valves to create pressure drops. That's not the function, like we would in resistors, where we may want to take a bunch of resistors together and make a voltage divider or something. I mean, technically, I guess you could do that with throttle valves, but there are other applications such as pressure regulators or devices such as pressure regulators that do a much better job. So we don't use throttle valves specifically to drop pressure. I guess you can if you want to fool around with this stuff, but industrial applications don't really use that for that purpose. Now we got variable, and that's the symbol for a throttle valve, check valve, and non-return throttle valve, which we'll get into in a minute, and we'll take a look at applications for that. What I want to do is I just want to say, okay, what about these lines? I did discuss earlier about the fact that is this a hose? Is it a line? Is it a tube? What is it? You can pretty much say that a tube is less flexible than a hose, and a hose is much more flexible. Moving forward, if we want to define a hose or a line, or even a tube, if it's a tube or a hose, it's going to show as a flexible item in your drawing. So this guy's going to be flexible. If it's a line, if it's hard line, it's just going to be a solid line like this. And of course, when we want to indicate in a pneumatic drawing that 2 lines are connected, we put a dot. And any kind of working pressure line is going to be solid. And let's get into this. Or it'll be flexible if it's a working pressure line. Let's get into this. This guy is a control line. Okay, so a dashed line like this type of dash is used for a control line. So all pilot lines are going to be dashed like this. Now, also, when we see a dotted line like this, that means that there's some kind of internal feedback that's going on. Now, I just want to talk about one more type of line before we go, and this is a long dashed line, and you'll see these very rarely, but they're for low pressure return lines. Now, in pneumatics, we don't really have low pressure return lines because the return line is just the atmosphere. We just blow air out of the atmosphere, out of the exhaust, and then the compressor sucks it back in again. But essentially, that's kind of a loop, right? Well, if we had some precious gases, if we were dealing with some gases that we paid a lot of money for, and we were in a scientific situation or a chemical process, and we wanted to collect those gases to recompress them or reuse them in our pneumatic system, we would actually have a return line that's going back into a tank. Also, for any kind of volatile gas that we're using, compressing, and we don't want it to go into the atmosphere, we want to grab that and put that back into the system. So in some cases, rare cases, you will see some kind of pneumatic return line. As I said earlier, these pilot lines or control lines are dashed. So I want you guys to start using those in your pneumatic drawings, in all kinds of schematics. I want you to use dash lines for your pilot lines. And essentially, it's just any line that goes into a pilot is going to be, or any control line is going to have dashed lines. And that's important to note. The pilot lines are dashed. And in this case, this is a pilot line, and that's why it's showing a dashed line. Now, what I want to talk about is controlling the speed of a pneumatic actuator. How do I control the speed of this? If I just put pressurized air in here, and there's no load, and I put pressurized air in here, like a 50 psi, it's just going to go wham! It's just going to fly out really quickly. But if I wanted to move slowly, but also I need 50 psi because I'm lifting something really heavy, I want to apply that much force, but I don't want it to go really quickly. How do I slow it down? Well, I use a non-return throttle valve. And the thing about pneumatics is, generally, we meter out in pneumatics. We don't meter in pneumatics. And I'll try and explain that. If I were to put pressurized air in here and there was no load, generally when there's no load or very little load, we always meter out. If there is actually a load on my pneumatic cylinder, it's okay to meter in, but it's just generally not a good practice. And you will see, you can play around with it in the lab. You can actually change metering in and metering out. And you can see there's more control of the speed of a pneumatic actuator if you meter out. Let's talk about why we wouldn't meter in if there's really very little load. Watch this. I'm going to pressurize air in here, and it's going to make this thing go, okay? So pressurized air in here, and it starts to make it go. Now, we will study gas laws a little later, but what happens is I'm increasing the volume. When we increase the volume of a space, the pressure goes down. Slightly, but it does. So what's just happened? Even though I'm still flowing pressurized air in here, the volume increased. So because the volume increased, the pressure went down slightly. And this thing is going to then jerk a little bit. It won't be a nice, smooth, even motion. It may show just a little bit of jerking, especially if the seal in here is really an older seal or doesn't slide that well. I mean, most seals are pretty good, but this, I mean, I've had this cylinder, I've been using this thing for 10 years, so the seal's probably not good in it anymore. I've been using it for demos all over the place, so I'm actually probably destroying the seal. So this thing actually might jerk a little bit if I put a little bit of pressure in here to make it extend. So if we want a nice even motion, what we're going to do is we're going to put a non-return throttle valve or a metering valve on the output. And now what's going to happen is that as that air is leaving here, it's actually under pressure to some degree because it's being throttled. It's being throttled. So that air that's coming out of here is getting throttled, and then as it's getting throttled, there's a little bit of back pressure, and that back pressure is actually slowing my cylinder down. And yes, to some degree, I'm losing a little bit of my force because I'm fighting, but it's very small and negligible. If you really want, you can add another couple PSI on this side. If your force is so specific, you really need to have a very accurate force, you might want to just go and actually measure that force and dial the pressure until you just get it right. Because that back force that's created from that pressure is actually going to play into that to a very small degree, but you may have been thinking about that, and it is kind of part of it, but very rarely do we actually worry about that. So we only meter out, we don't meter in, but in hydraulics, because hydraulic fluid's not compressible and the gas laws don't apply, and as I increase this volume, the pressure inside this area here doesn't drop, then actually we meter in hydraulics and we meter out in hydraulics as well. But generally in pneumatics, we stick to metering out. So this is just an example here where let's just say I want to put just a metering valve on. Now, this is really walking you through why we need a non-return throttle valve and why we don't just use a metering valve. So this is the situation here. So what I want is I want this thing to move slowly on its way out. Okay, so a throttle valve can slow the air down and it will do what I just talked about, slowing that thing down. But now that'll work in extension. This particular situation, if I put a throttle valve there, no problem, it'll work just fine. But what about in retraction? What about when I tell this thing to start to retract and go back this way? It's also going to be throttling it. And actually, it's going to be metering in, and I don't want to do that. So what I do is I add a check valve. Yeah, really cool. Add a check valve here, and this allows air to freely flow through this way so that the air going into the cylinder, in this case to make it retract, is going to be free flowing. It goes right through the check valve. We know it loses a little bit of pressure, but that's not a big deal, like 2 or 3 PSI. Lose a little bit of pressure here, and this retracts, and it retracts just fine. And it can go really quickly. But when it is extending, the air coming out of here, it sees the check valve and it sees the metering valve. And just like electrons find the path of least resistance, so does air. So air's going to go here and it's going to go, okay, I'm seeing this check valve and actually there's like a lot of resistance there. I cannot go through this. So I'm forced to go through this throttling valve. So it's forced to go through the throttling valve and it gets throttled and it slows the cylinder down in extension. And that's how non-return throttle valves work as metering valve. So whenever we meter a cylinder, we're controlling its speed, and we always meter out in pneumatics, and we use a metering valve, which is a non-return throttle valve in application. I was going to show it to you, but I lost it. There it is. Non-return throttle valve in application. Often these are actually just screwed right into the side of the cylinder, and we can do this, although we do have inline metering valves as well, and they look like this. Whoop. They look like this. So this has a check valve in it, and it's got a throttle valve in it, and it's a non-return throttle valve. And if we use it to control the speed of a cylinder, then we call it a metering valve. So here we go with an operation where I'm metering on both sides. And we just quickly run through this, and we can see that if I want this cylinder to extend, the air goes here, and it sees this, it pops this. It will not go through this throttle valve because it takes the path of least resistance. It goes right through here, and it goes to extend the cylinder, but we can see that it's going to be metered when it comes out, because when the air on this side of the cylinder comes out, it's going to be metered because it's going to see the check valve, and it'll be forced to go through the metering valve. And the opposite happens, where we're going to make the air go this way and retract. It's going to go right through this guy, and it's going to be freely putting air into here, but this air is going to be throttled. And by the way, when you're looking at these metering valves, like maybe if I give you an exam or a test or something, you can always see whether or not the throttle valve is positioned properly, and pardon me, the metering valve is positioned properly by looking at the check valve. However you look at it, that check valve is always going to be pointing to stop the air coming out of the cylinder. Yeah, so I may just actually put, like on a test or a quiz, one of these upside down and maybe see like, what's the problem with this? Yeah, watch for that. So just think about this. If you're wondering how to check this, how to actually put one of these onto, if you have an inline, you have to think about it. You have to put it so that it blocks the air leaving with the check valve, and it's forced to go through the throttle valve. Let's just talk about another symbol, and then we've got a couple other symbols to look at, and then I'll let you go. So this is the symbol for an accumulator. Like I talked about before, I had my accumulator here. It's just a small air tank, and we use it for like backup pressure, emergency pressure sources. It's very much like a capacitor, and it deals as a kind of a shock absorber, and we can use it for pulsation dampening. Pneumatic timers, yeah, really cool things. Pneumatic timers, yeah, dude, there are pneumatic timers. It's really cool. And essentially electronic timers just use capacitors. Pneumatic timers use these things, accumulators. Pretty cool. And we can also, again, use this with a shuttle valve to be able to deal with low pressure systems if we have like a loss in the system. So accumulators are just small pressure vessels for just kind of little small applications, very much like a capacitor in electrical circuit. Now, a pressure relief valves are very important, and there are lots of different applications. Essentially, you can look at it like this. If you have a system somewhere in a pressurized system, in a bunch of pneumatic lines going wherever to actuators, it's a pneumatic system, and for some reason there's an overpressure somewhere. That overpressure can do some real damage, especially if it gets into an actuator that's designed to only specifically apply a certain amount of pressure. If there's too much pressure in the system for some reason, then that actuator is going to be applying too much pressure. And we can blow systems out as well, because lines and connections and hoses and NPTs are only designed for a specific amount of pressure. If I have an overpressure, what I'm going to do is I'm going to put in a pressure relief valve, and in this case I've got one that's adjustable because it's got my arrow. You can also get them fixed as well. So I'm going to adjust this to whatever pressure I need it to be to allow a release. Now, one application for this is this. If I have a back load, heavy back force on the load, that actually can create pressure in my system, and we can see how that's creating pressure in the system here. And then if I'm telling this to extend, then I've got my air pressure here that's coming from my regulator, that's coming from my compressor here. That air pressure is here, it's going through my valve, and it's making my cylinder extend. But if for some reason I had a heavy force, like a jerking force, or maybe some other thing, was lifting a weight, and something happened that extra weight got put on top of it. It's pushing down. It creates extra pressure in the system, and it's back pressure, and this thing is going to release it, and then it'll just vent out, no problem. So a little bit more ancillary equipment, some symbols, and then I'm going to let you go. Here we have some valves. These are on and off valves. These are the only valves that you will see that only have 2 ports. All other pneumatic valves are going to have an exhaust port. In this situation, we're just turning air on and turning air off. This is a ball valve, which is just pretty much yes or no, on, off. The other valve over here is a basic manual valve, and yes, you've seen those to deal with the I was going to say airflow, the water flow in a garden hose. Yeah, so we have these in pneumatic system as well. We also do not use these for pressure control, but we use them for flow control to some degree. But essentially, it's when you want to kind of vary the turning on of a pneumatic system, especially if you don't want to jerk your pneumatic system on. You want to slowly kind of turn that pneumatic system on. So it's going to be like kind of a throttle valve as well as a valve that's turning something on and off. And here we go with our last slide. Just some more symbols that I want you to be familiar with. And again, a tank. And this is, you see it's a little fatter and a little larger. That's going to indicate a pneumatic tank as opposed to a pneumatic actuator. This is a quick disconnect coupler, quick disconnect like that. And this is your pressure relief valve, which is adjustable, and that was on the symbol that we saw before. Silencers are really very important. If you have ever actually pulled up beside a truck on the road, and especially in the summer, if you had your window open and you hear this psh, even the buses do that as well. Any vehicle, large vehicle with air brakes are constantly pressurizing the system, and then when they pressurize the system and it gets too high, they vent. Actually, when the compressor turns off, it vents, and it actually vents that extra high pressure that's in the cylinder head. When you turn any compressor on or off, when you turn them off, as soon as you turn them off, you hear this psh, that is air coming out. It's actually pretty loud. Air coming out is really loud. Like I said, like if you ever been beside a truck or something and you had your window open, it's almost shocking how loud it is. So silencers are really very important, and they're on all kinds of pneumatic actuators. Even any exhaust on a valve will have a little tiny silencer on it. Now, this is a pneumatic air supply. It's round. You will also see pneumatic air supplies, for instance, in Automation Studio, that are little triangles going in. There you go. That's enough about ancillary equipment and symbols. And moving forward in this course, I'm going to refer to these, and we'll just maybe learn a little bit more of these as we go. But I just wanted to introduce you to all of this terminology and the applications. Thanks for watching. Goodbye.